Now, today's topic is, you know very well, designing with carbon, the creative power of organic chemistry. We all know that carbon is very unique. It is a versatile element, no doubt about it. Designing with carbon, as Professor Agasti says, remains the driving force for chemical and biomedical innovation. As far as the element carbon is concerned, it is a unique element in the sense there is an entirely exclusive subject called organic chemistry related to carbon. This is unique about it. And hydrocarbons, you know what role they play and what impact they have in this world. And the design principles of organic chemistry, no doubt, are shaping today's science and technology landscape, no doubt about it. Notwithstanding battery-powered vehicles, still hydrocarbons are very important, not only as fuels, but in many other fields. Okay, so carbon molecules, some of the things, I don't want to preempt. Anyway, he is going to mention about many carbon molecules which are lighting up the diseases, that is in diagnosis and such things. So let me say a few words about Professor Sarit Agasti. Once again, let me tell you, he was kind enough to accept as soon as we requested him. Professor Sarit Agasti had a very bright and illustrious academic career. He obtained his Bachelor of Science UG undergraduate degree from Ramakrishna Mission Vidya Mandira, Belur Math in Kolkata during 2000 and 2003. He obtained his Master of Science degree from IIT Kanpur. Okay, then he went to United States to do his PhD. He obtained his PhD from the University of Massachusetts, Amherst. Okay, then he was a postdoctoral fellow at the world-renowned Harvard University. During 2011 to 2015, for about a decade, he was in the United States. And Professor Sarit Agasti joined JNCASR, Jawaharlal Nehru Center for Advanced Scientific Research, founded by Professor Bharat Ratna Professor C.N.R. Rao. It is in North Bangalore near Jakkur. And he joined there as an assistant professor in the new chemistry unit and chemistry and physics of materials unit there. And now, from 2021 onwards, he is the associate professor at new chemistry unit and chemistry and physics of materials unit. And, you know, he has about 90 papers to his credit, in fact. Okay. And his research areas include organic and supermolecular chemistry, chemical biology, fluorescence imaging, and super resolution microscopy, and sensing, diagnostics, and drug delivery. Oh, such wide subjects, really. And I'm sure that he's going to cover all these areas during his talk, about which we are all eagerly waiting. And once again, thank you, sir, for accepting. And Sharanya, please.
Thank you, sir. We have a small memento from JNP side, which I request our director to give to the speaker.
I want to mention, as I did in the case of earlier lectures, this is chemistry in action, this memento. This is the model of a rocket, Bahubali rocket from India. Both organic chemicals are there present in this rocket as propellants. Thank you, sir. Thank you very much. The stage is yours. Please.
hello everyone. So I'd like to first thank Dr. Guru Prasad for a very nice introduction, and I must tell you that I was so amazed to see that this planetarium got a director who is so interested in science and technology, and I must congratulate him for bringing science to the common public. And I think it's very rare insight that we have a person who is loving science and leading this institute. So, and it's my pleasure that I can be a part of this journey what he started, right? So I'm very much I will sure. Okay, so with that, so my group does research in organic chemistry, I just discussed, and we are located here in Jakur campus, right, JNCASR, and I have an active group, and so I thought that couple of my group members are also here. So the respective research area what they are working on, so they will also be talking to you and give you a glimpse that what are the kind of research is undertaking where carbon or organic chemistry is going to be useful for. So it's going to be a joint effort of my group, right? And they are the PhD scholars, and they are doing research in a very advanced areas what you will see. Along with that, we also managed to bring you some attractive quizzes, right? So we are going to after half of the presentations or 1/3 of presentations, we will be conducting a small quiz session via online. So please make sure that you have access to the mobile, so it will be completely online, and we will be calling the winner of that quiz sessions in the stage. We will give you some Diwali gift, so that make sure that you pay a little bit more attention and know what's going on, right? And hopefully you'll have a good time in next 1 hour or so. So with that, I think let us start with sort of the topic, or the discussion is looking at how we use carbon and use it to the creative power of organic chemistry, right? And I think this term carbon is very common, and organic chemistry is also very common. I think many of you may have heard this topic, but what I'm going to tell you is what is carbon, right? Just let's have a look. So this is basically all organic compounds are content the carbon, right? So this is the element which we're keen on, interested, and what's so special about the carbon, right? So no other element matches carbon's bonding versatility, right? So anything to do with the bonding, like let it be human bonding, let it be carbon, I think once the bonding happens properly, then only magic happens. And I think that carbon represents one of that unique property. So it has, in this element you have 6 protons, right? And more than the protons, the important things are the electrons which are rotating here. And you can say there are 2 core electrons and 4 valence electrons, right? So probably the textbook knowledge many of you are having, right? And this 4 electron, which is essentially the thing which magic happens. And let me tell you, this is an element which is which has reactivity as well as abundance and abilities to do diversity of bonding. Let us look at some of those examples, that where are these carbon or the organic chemistries are combined together, and where all of you must have experienced or must have used one of these things. I think all will know that organic chemistry is probably the basis of all medicinal chemistry. Any medicine you take today contains some contributions from the organic chemistry. Let it start from a painkiller all the way to advanced medicine like cancer therapeutics, right? So all are built from carbons from organic chemistry. We all know this. OLED, you go to any supermarket, you go to any of these Reliance Digital, Chroma, and you see nice LED screens, what everybody wants to have it, right? built and research developed by organic chemists, right? And you can see these molecules. So these are the molecules which are built to make OLEDs, and all based on carbons and some of the compounds which showed here. More importantly, what about organic molecule in disease diagnostics? So many times what happens that you need to locate the regions where there is an abnormality, let it be development of something like an disease cancers, or there is a blockage in heart, or any other sort of abnormalities in the bodies. Once someone goes to clinic, how do you know that which part of the body is having the problem, which artery is blocked? So they need to inject a specific type of dyes or contrast agent, and that has to be built by organic chemistry. And here is an example. What you saw here is that these are the molecules. You see indocyanin green. This is a very, very important molecule, and you can see these nice blood vessels when it is injected a person during the angiography, right? Again, these are the molecules built specifically to diagnose a disease and essentially treat and save a life, right? And these are the kind of setup what goes behind, and my students will talk more about it, but what you can see is that here essentially once a person is injected with these molecules, you can excite this with a certain light. You should be able to see nicely on the background of any other interference this nice highly bright fluorescent molecules, which tells you whether there is a presence of blockage or there is a presence of tumor, which is nicely highlighted, right? So that's the power of organic chemistry what we talk about, starting from any medicine all the way to your daily life. Your mobile phone screens are made of nowadays with OLEDs, your computers are made of OLEDs, all the way you go to any diagnostics, you use that. Not only that, you can think about a sustainable future, right? We are all worried about plastics, like you go anywhere, you see a garbage pile. What about having a biodegradable plastics? And who are contributing to make that? This is the knowledge of organic chemistry. What you can clearly see here, polylactic acid, PLA, polyhydroxyalkanoids, thermoplastics, stretches, right? All of them are built from organic chemistries, but these are also derived from certain plants, but they can only made and processed for the use of plastic because the knowledge of organic chemistry, because people know how to use them, how to make them, how to manufacture it in an industrial scale, right? So you can clearly see all over the space, every day we are surrounded by this organic chemist and its use. And while I was talking to Dr. Guru Prasad, he also mentioned me that there is a vast area of propellant. We were just talking just before the talk, and I'm sorry I didn't put that, but it is your expertise. Maybe next time you should talk about that the propellant which is used by almost all the rockets for our ISRO has organic chemist who builds these propellants for specific use. Let it go for the moon or let it go for other missions, the kinds of propellant required are all built up by organic chemists. I was truly fascinated by knowing that, and I think next time I would really like to put that in my talk also. But very nice. So with that, let us see a little bit more details that what about this carbon, and little bit more background knowledge or basic understanding that what we are talking about, because it's a broad wide audience. So let us look at what does this mean. So once we think about carbon, we think about these 4 different sort of bonds organized in something called a tetrahedral arrangement. So this is basically the carbon which bridges A, B, C, D, 4 different atoms in this case, and they make the molecules. And the important thing is that a carbon can bond to another carbon or another atom via a single bond, okay, or it can be added together via something called a double bond, or even it can go something like a triple bond. And as you can clearly see that as we go from single to double, triple, the distance between carbon to carbon decreases, right? And also the geometry of the arrangement of the other atoms around these is also changes, okay? The angle, the way it is attached to the surrounding other atoms are also going to change. That is going to be apparent in subsequent slides. So that gives you abilities over many other molecules like nitrogen, silicon or many other molecules, the abilities to form variety of bonds with its own as well as any other atoms, and that's essentially it. So if you think about the versatility, stability, abundance and connectivity, the carbon emerges is one of the nature's choice to build the life, right? Is all of the sort of molecules or organic molecules which you are built of, like starting from protein to a DNA to a metabolites, right, a cell, which is all made of this carbon and organic molecule, right? And it's the nature's choice. So if we want to do and drive our science, I think we need to rely on nature and think that that is what we are going to use it to discover the next generation of science. So based on this bonding diversity, the secret behind the life, we can actually create molecules and materials of different kinds. And as you can clearly see, the arrangement of the carbon in here is very different than the arrangement over here, right? And one very important thing what you can clearly see that all we have used these pencils, right? And once you slip the pencil, a layer of this carbon is usually separated from the another layer. So it's basically slips, and that's the way you actually mark something on your paper, right? So how beautiful is that? That the property of the molecule such a way that it gives us abilities to write. Then there is in graphene, it's sometimes called a wonder materials. Many of these previous lectures might have talked about this. So this is a material which many of semiconductors, new phenomena is coming up. So this is a molecule which is called fullerene or C60. Again you can see it looks like a football, right? It's called a buckyball, and again builds up by the carbon. Then there is nanotubes. Let me tell you, this is the nanotube which is now constantly used to make fibers of the highest strength, which is used many times in badminton racket and many other places to strengthen the materials. Okay, so what are the different kinds of carbon molecule we have? So as I told that you have a carbon attached to it 4 different atoms. Then you can have another carbon attached to it along with hydrogen. Then you can also have, as I told, the bond between these could be double bond. And as you can clearly see, the angle here is now 120, whereas here was 109. And one of the depiction over here. And this is the sort of double bond I was talking about. So you have 3 atoms attached in a 120 degree. Okay. So carbon skeleton diversity, what you can see that based on the number of molecule attached, you can have high length, you can have branches, you can have introduction of double bond, and you can also make molecules which are connected together in a ring. For example, cyclohexane or benzene and things like that. Okay, so there are also things like isomers, like the molecule structures or compositions are same, but they are different in terms of their bonding. You can see this is linear, but this is connected like this, right? And there is also something called an enantiomers, where are exactly same connectivity, but they are mirror image to each other, which are again the basis of many life. And there are something also called the functional groups, so where there are different kinds of molecules or heteroatoms. So these are oxygen, or they are sulfur, nitrogen. They can also combine together and make a new molecule. For example, the basic building block of life is amino acids, right? So they many times utilizes like this carboxylic acid as well as amino heterofunctional groups, right? So not only they can bond together, they can also make structures by bonding to the other element, right? So that's sort of diversity what we have. So now what I say that you need to always think positive, right, like a proton, because and think like a proton, always positive, so that you can assemble different elements of organic molecule and make new molecules which are called, for example, an caffeine or an ibuprofen of many kind. So I will now tell you a little bit story about the from carbon to cure, right? So this is an area which is very relevant to daily life, that medicines, right? Every time we feel an headache, we feel fever, we feel body pain, we try to go and check for medicines, for example paracetamol, right? Sometimes we take aspirin, right? So let me tell you a little bit story on how one of the important organic molecule is aspirin, right, which is one of the highest selling painkiller, and how this has been developed. So it's ancient, like 4,000 years ago, people used to use the bark of a willow tree, okay, and what they have found, that if they are having a fever or pain, and if they take the bark of the willow tree, they are actually relieved from the pain. And that's probably one of the first observations of the painkiller, what was extracted from this. But at that time it was unknown to us or anyone that what are these molecules and what is the active molecules I am taking, right? So people start investigating, and Hippocrates, as the father of the modern medicines, he also prescribed that, if you take these willow bark tree and the tea made out of that, you can essentially have fever reduced. Then Edward Stone experiment, where he actually in mid 18th century he was able to isolate the exact molecule which was responsible for that, which is called the salicylene, which is the extract of this bark. And you can see again a very nice organic molecule. But unfortunately this was happened that this can also be extracted from the meadow sweet producers of salicylates. So this is salicylene from the willow tree, and this is from the salicylic acid. So these two becomes the most important ingredients which is responsible for the reducing fever or the pain. But the challenge was that this molecule, once someone takes, they started to have side effects, right? For example, they started to have stomach pain. So in that, around 1830 or so, the organic chemists were searching that how to have the same effect but reduce the side effect. And there the pharmaceutical company and organic chemist comes into play. What they did is that you can see the structure here is one functional group. They just changed and attached another functional group over here, which is called the acetylations of the salicyldehyde, and that again exactly reproduced from a starting material which is phenol, which can essentially be extracted from the the crude oil. So now initially we started extracting from the nature, but for mass producing you really need to do it in a lab in a scale which can be accessible for everyone. And that's exactly this was possible by the Kolbe synthesized salicylic acid, and finally the salicylic acid is refluxed with acetic anhydride called acetyl salicylic acid, right? So you can clearly see that we had a medicine at 4,000 years ago from the nature which works but has lot of side effects, not available to the sort of mass produced. And then by the beauty of organic chemist, we now have a medicine which is modified with loss of the reduction of side effects, improvement of the benefits, and produced in the laboratory so that it is accessible to almost every people, and you can go to any market and buy this. And not only that, these are now have been modified. Now you see from that small molecule we are able to build a large number of molecules from its derivative to analogues in cancer therapy, right? So same medicine which was available there is now used to reduce heart disease, because this is now reduces the blood clots. This can be targeted to the cancers to reduce cancer burden, all the way to many different varieties. And only thing changed here is the structure around this molecule and introduction of new groups by organic chemists, right? So that essentially tells you that where we stand today. And here are some of the examples. As I told, that this is the whole skeleton of the molecule I am talking about, the aspirin, then which is used for sort of reducing pain, fever, molecules of medicine. Then there is benzyl penicillin, right? Many times it is one of the wonder drug which is for antibiotics, right? Again, developed nicely by organic chemists for bacterial infections. And now you see, this is another molecule called paclitaxel. It is one of the first line chemotherapeutic agent for treating cancer. See the complexity of this molecule, right? And now these are all built by organic chemists by connecting bonds together to give you exact structure what we are talking about. Just think about the sophistication which is necessary to do this. Okay, so this is an anti-cancer drug. So little bit more deeper that, what is our understanding to the process of organic chemistry. We say that, okay, we mix A, B and make C, right? But can we plan something? Can we understand what goes behind this so that we can make a molecule of our own, of our design? So that's how we need to know that how the mechanism, how the chemistry happens. And although if you take this acetic anhydride and salicylic acid together, you will get aspirin. But these are the steps which day and night we learn, we study in laboratory to tell you that if there is a problem in any step, how to troubleshoot it. If there is a new compound required, how to go about it. But without the knowledge of whole of these, it is impossible to proceed. And this knowledge what we gained is now reflected to make extremely complex molecule, right? Here you can see it's impossible for us to imagine that it has gone to a details where we have a molecules build up with some 20-30 steps, takes decades. So we started with very small molecule on 1897, and now we have the abilities to make molecules in these complex states. And that's how we now benefit to make molecules to treat disease in bigger and bigger complexity. I think with this I would like to move to molecules that lights up life. For that I would like to, we'll have the quiz. Okay, so I think the first part, as it over, we have a very small quiz, and I request Alka, so she is a PhD student, to sort of conduct the quiz. So I request that if you have a mobile phone, you can go to a website called Kahoot, Kahoot, right? So we'll have question popping up here, and you will have few seconds to answer. Whoever will be answering first will get the maximum point, and will display the name. And I would request the person who is the first to come on to stage and introduce yourself, and would like to give a small gift. Okay, so you want to start? Okay, so can you go, please go to this Kahoot.it, Kahoot.it, and then once you go, you can write this game pin, or you can scan it also. You can.
So basically you can just scan the code and log in into your mobile, or else you put the password by downloading the app itself. And this is the trial one. 2 questions will be trial, so that all are on the same page, and then we'll start the first round.
Yes. you can use my mobile.
Yeah.
If you want to come here, you can use my mobile or her mobile. You want to come here? Please come here.
You can come here. Yeah, it will direct you to the link. Go to the website. You can chat just directly. You
I think all of you are good.
remember to write down your name so that we know who it is.
You don't want to miss your name to be appearing here. Okay. Okay, good. So it's like fastest finger first, right? So if
Yeah.
you know the answer, you must do it quickly. And okay, let's get started, Alka. So, so the question will appear, and it will also appear in your mobile, and you must answer there. So, which city is the capital of Karnataka? This is trial question.
Yeah.
Okay, so all are awake and good. Next.
So we'll get the scores like this. Whoever has like done it very quickly, so will be awarded more.
Yes, okay. Who is known as the father of the nation? So, okay, someone gave wrong answer. Maybe by you want to do it quickly. Okay, so we'll go to the.
Just a minute.
Okay, so now the real quiz. You just have to. You can stay in the app, or you can just go and then. So there are how many quiz, Alka?
3 quiz.
3 questions. 3 questions are there. $23. I think 3 is still someone waiting. 24, 25. Everyone done? Anyone waiting? I think we had 27, right? Or 25? 29? All entered? Anyone missing? Done? Okay. So, okay. The first question is coming. The question is on the top. I talked about it little more details, I think, right? Oh, okay. So we have 12 people. Mocks. Okay, good. Wow, nice. 19 people. Oh wow, I think Mox. Let's see the third one. Nice. Oh, Anubhav. Who is Anubhav? Okay. Now close competition. This is also discussed. Saina. Third, second, Jubraj. So can I have Mox on the stage? So we'll have a small Diwali gift from our side. So he can choose. I think we have 3 options of chocolates. So you can choose which one you choose. Okay. Can we take a picture here? Yeah. Alka, can you take one picture? So can you just tell where are you coming from just briefly? Wait, just good. Can you tell where are you coming from?
I'm from Bangalore. I'm 16 years old. I'm a self-learner. I don't go to school. I'm in 10th grade right now.
Okay.
I attend regular programs at the planetarium, including the weekly high school classes.
Let's congratulate you. Nice. Congratulations. Okay.
Thank
All
you.
the best. Okay. I hope all of you enjoyed this, and you will have 2 more opportunities to participate and come onto the stage. But with that, I would like to request Ritika to speak about the molecules which lights up the life.
So, good evening everyone, and welcome to Dasara Lecture 2025. So, before starting my presentation, I would like to thank Jawaharlal Nehru Planetarium and my supervisor Professor Sarit Agasti for giving me this opportunity to present some slides in front of you. So, I'll be talking about molecules that light up life. Now, like listening to the name light, what could be a better day to talk about light when Diwali is coming on way, where we light up diyas, and then we like decorate our buildings with different colors, which you can see like painting buildings with lights of different colors. And then, you know, lightening up lanterns, which again adds beautiful charm to our Diwali celebrations. And yeah, bulb, which we use regularly in our lives. So the one thing which is common in all these beautiful pictures is they have their own light. Now, there are some organic molecules which also have their own light. So you can think of it as, you know, we like put a string of light on Diwali and all having little bulbs. So these molecules can be those little bulbs which can light up. Now, this glowy liquid is tonic water, which is present in our daily life, and you can see how beautiful they glows in a dark when you irradiate with a blue light present in the background. So this you know, this molecule which is responsible for this glow is quinine, and this is the first molecule which was, you know, found out that could emit light. And the structure is very simple, a small organic molecule capable of emitting so much of light which you can see through your naked eyes. Now the scientist behind discovering this molecule is Sir Frederick William Herschel. So in 1845 he was sitting in his living room and he observed something very unusual and beautiful. So he saw a glass of tonic water, you know, emitting light, and it was like appearing a glowy kind of thing. So he was luckily sitting at an angle where a sunlight from the window were falling on the glass, and he was sitting at the right angle to that, and he could see the glow that this solution was producing. So from there a lot of advancement happens, discovering a whole lot of new molecules and a new kind of microscopes to observe these molecules. Now labs which work on these molecules, they have, you know, very commonly available these glowy kind of liquid or glowy molecules, but they are not limited to labs, but they are also present in your kitchen in different forms. You know, eggshell having a protoporphyrin molecule which emits a you know, red light, and then honey has like multiple aromatic fluorophores which can emit light. Now olive oil, turmeric and highlighter ink, and then detergent, tonic water, as we have seen, all these can emit light. And also, you know, in your home you can make a setup where you can create a dark cardboard box and then add these, you know, solutions, the liquid form of these solutions in a cuvette. Maybe you can use a tic-tac box to create that cuvette, and then put a camera of your mobile phone at a right angle to it to observe and capture some beautiful images like these. So now the question comes, why not all organic molecules emit light? So there is some chemistry involved because of which only few molecules can have this property of emitting light. Now, how an organic molecule can behave in light? So first, some molecules don't have any interactions with light, while some other molecules which can absorb but cannot emit. Now there are third molecules which can absorb light as well as can emit light. And now these two we can discuss here, why some absorbs while do not emit, while the others which absorbs in addition to which they emit also. So you can see these molecules can go to an excited energy state by absorption of light. Now the question comes, how will they relax back? So the first choice available to these excited molecules is releasing via emitting heat energy. So they will emit heat energy and, you know, relax back, but they will not emit any light. While they have a second option, they can come back to the ground state via emission of light, and such molecules is what to our interest, and these molecules are called fluorophores. Now this molecule is indeed comes back by emitting light, and this is a well known molecule present in our inks which we use in our highlighters to highlight our textbooks and, you know, notebooks to read them further. So the basic principle which is acting behind the emission of light is, after exciting these molecules with light, the electrons goes to a excited state, and then from there they comes back to the nearest lower energy state, and from this state they come back, and as a result of it you get another light. So there is, you can see, energy difference between the light which is absorbed and the one which is emitted. So that's why you irradiate it with one color and then you get the other color because of this difference. So like suppose if you are irradiating with blue color, you can get maybe a yellow color. So like this you can create different kind of molecules emitting in different colors, and that's where organic chemistry gives you power to tune the colors, and that's how you can paint the molecule with different colors, and you can create color of your own choice. So now you can see these are simple organic molecules. The yellow color represents that they will emit in yellow color. These red means they will emit in red color, blue, green, and all those colors. But these molecules are made from the basic building blocks. So it depends on the organic chemistry which you are using to connect these molecules to make a full grown molecule which can now emit in different colors. So this quinine molecule, as we have seen, this emits in blue color. Now this is fluorescein, this emits in green color. Then this rhodamine B, this emits yellow light. Now this pyridine 1 molecule, this emits in red color. So basically you can paint your canvas with different colors using basic organic chemistry, where you can create molecules which can emit color of your choice. So if you see these cells without these small organic molecules, you will see a boring one color image where you can see the dynamics, but you cannot really see them in different colors. But if you add these small fluorophores in your cell, then you can better differentiate between different regions of the same cell, like this blue region and orange region. You can differentiate just by using different colors. And here you can see this cell dividing from 1 to 3, which can be easily and beautifully can be observed using these fluorophores. And also the question comes, how do we attach these fluorophores to the target of interest? So there are antibodies which are very specific to their target, and in that you can attach the fluorophore which will bind to your target, and as a result of which you can see the beautiful fluorescence image. This is example of a white blood cell which can be seen through a simple targeting strategy using fluorophores. Now how can we visualize? So in normal labs we use simple microscope where one light comes from the source and falls on the sample kept below an objective, and after getting excited they will emit light, and that can go to either eyepiece or the camera, where you can observe these cells or your any biological sample targeted with fluorophores, and as a result of which you can see like these beautiful images when you observe or capture them through your camera. So these are different biological cells or tissues. This is neuron cell, where you can observe each and every part of the same cell with different colors. Now with that, what we can say in conclusion is, light makes our life beautiful, and there are organic molecules which can emit light of their own, making it more beautiful, and then you can paint your canvas with different colors using simple organic chemistry knowledge. And then you can make the colorless biology to a colorful variations where you can see them more beautifully and more conclusively. Yeah, thank you all for your attention.
We have the second round of quiz. follow the same process. So let's go to the same website.
You can put it in pocket. This one. Yeah. So same way you have to scan it. So much of disturbance, no? Disturbance. Okay, let's start with the first question.
Which was the first small molecule fluorophore discovered from natural sources? Who is H? Oh, nice. Okay, next question. What happens when a molecule absorbs a photon? Next. DHK. Oh, okay. The new outline.
Wow.
Wow. Everyone is paying attention, great. That's good. Okay, very important one now. Wow, that's great. So we have Radhika, third place. Second place, Kritik. First place, DHK. Let's
Who's
clap
that?
for DHK. And may I have you in the podium? Your choice. Which one would you like? Yeah. Okay. Can you please come?
Okay. You can introduce yourself first.
Thank you, sir.
just tell about where you coming from?
Okay, my name is Dharmapuri Hiren Kumar. I'm from Bangalore and I'm a bachelor student attending the reprogram here at the planetarium.
Okay, so for the third part, I invite Alka to continue with the next part, where we are going to talk about a Nobel winning chemistry called click chemistry, which won the Nobel Prize a couple of years back and has been one of the important discoveries in many ways, starting from medicine all the way to making polymers and many other things. So we'll have Alka talking about it.
So I'll be discussing about, like as Ritika has discussed already, about the fluorescent emitting organic molecules. So I'll discuss more about like how can we combine these molecules to make a fluorescent molecule or something like drug molecule, which I think sir has already explained a lot. So this is a very basic chemistry they have done, but it has a very huge importance, and that's why they have got the Nobel Prize in the 2022. So as you can see in the picture itself, they're combining the molecules like a seat belt. In the seat belt we are combining the two handles, and it looks like simple, but I'll show it's really very simplistic and the idea is very novel. So there are so here we have the three Nobel laureates. First one is the Professor Sharpless, who basically pioneered the field of the click chemistry, where you can achieve simply these molecules combining together, and it is very easy and reliable and repeatable. And the second one, Professor Martin Meldal, he has basically worked on synthesizing these azide alkyne, synthesizing the click based molecules using the azide alkyne cycloaddition using the copper. But then in the cellular environment, as we know that copper is toxic, so Professor Bertozzi has played a very important role, where she has not utilized the copper and she has utilized the click chemistry in the cellular environment, and which is not even toxic, and she is able to label the cells, membranes, and she can even put these molecules inside the cells as well. Then moving on to like how it happens, let's say suppose we have a reagent 1 and we have a reagent 2 which we want to really combine. So it happens just like a click, these molecules will combine and we'll have the product in hand. So what are the advantages? As we can see, it is very simple, it is very fast, and it is very high yielding, and it produces minimal byproducts. Also it have the very important property is it is very selective and very specific. As I'll be showing in the next further slides, it is very much biocompatible. For living systems we can utilize this strategy. Then coming on to the animation, like I will show how it happens. Like let's say this is your click handle, the first reagent which I have shown in the previous slide. We will have a complementary another handle on which another molecule or some protein can be labeled. So it will come and specifically bind to it, and once these are injected into the mice, where thousands of other biomolecules are also there which are ready to interact, but still it will happen only specifically and to the complementary handle itself, not interacting with the other molecules present in the living system. So the next question is, just a minute. So the next question is, what could be these molecules on which these handles are attached? So these could be any drug molecules, we can attach it here. we can have the optical probes, we can have the MRI reagents, nanoparticles or PEG linkers, or whatever molecules you want to combine. It could be like 2 protein molecules you want to conjugate, it could be 1 DNA molecule as well as 1 protein you can conjugate, 2 different molecules itself you can conjugate onto the membrane also. So you can utilize this strategy to conjugate the molecules. And looking on to the video animation, like let's say this is the membrane where we have these yellow color receptors present, and these antibodies will come and bind to these receptors specifically, which are on the head, are labeled with these handles. So one complementary handle which is conjugated to the fluorophore will come and bind to it specifically, and will get the fluorescent signal from there itself at the specific positions. So so now comes the question, like, okay, we have seen the beautiful videos and the applications and advantages, but what is exactly the chemistry going on? So let's say this is my X molecule which is conjugated to some protein or some molecule, and we have a Y molecule which will combine and shows the click chemistry. So there are basically 3 types of click reactions which we usually discuss. One is the strain promoted azide alkyne cycloaddition reaction, where we have the protein molecule labeled with the azido molecule, and we have the cyclooctane molecule labeled with another molecule of interest, and then the click reaction happens and we get the molecule combined. And the other one is the copper catalyzed azide alkyne cycloaddition, where instead of the strained alkyne we have the simple alkyne, but we need to add the copper into it in order to get this reaction done. Then third one is we have the inverse electron demand Diels-Alder reaction, where we have the transcyclooctane as well as the tetrazine, and we can have the same reaction out of it. So this is the chemical aspect if one wants to look into these kind of reactions, like what is exactly the chemical buildup and how it is going on. So yeah, that ends the talk.
Next part I will invite Sasha. He will talk about that now we know that molecules can be combined by making carbon-carbon bonds, which are called covalent bonds, right? But there is a new type of chemistry which is developing based on organic molecules, which can be bound together by non-covalent bonds. These are like really weak bonds, but once you make many of these weak bonds together, you essentially build up a new sort of strong bond. Okay, so these are the basis of this called host guest or the supramolecular chemistry. And let me tell you that in our body most of the molecules actually utilizes this non-covalent chemistry. The beauty of this non-covalent chemistry is this reversible, right? So what do you mean by reversible? Whatever we came here from home, reversibly we have to go back to home, right? We are not stuck here, we are not into one direction, right? We can always go back, right? Maybe this is what is the life all about, that there is always a possibility to become new, always possibility to reverse things. And that's why the non-covalent chemistry is important, because if it is built on the covalent chemistry, we will be moving only one direction and life will not be as beautiful as it is now. So with that I would request Saswat to tell us that how this chemistry works when it comes to non-covalent chemistry.
Good evening everyone. As sir told and Ritika and Alka also presented, so till now we have seen how using a covalent bonds and covalent interactions we can make different kinds of molecules based on from a single carbon atom to different organic molecules which have different applications. But there is another field which is very actively emerging now. So it is based on the non-covalent interactions, how we can make different molecules. So so this is called supramolecular chemistry beyond bonds. So what is a supramolecular what is a supramolecule? Also it is called supermolecule. So how it is formed? Different organic molecules comes together and by the verge of this non-covalent interactions they form different molecular complex, and these molecular complex are called supramolecule or supermolecule. In 1978 Professor Jean-Marie Lehn coined this term supramolecule, and in the 1987 Professor Charles Pedersen, Professor Jean-Marie Lehn and Professor Donald Cram got Nobel Prize for the development of these supramolecules. So how these supramolecules form. Small organic molecules comes together in the reaction medium and they react with each other in the using non-covalent interactions like hydrogen bonding, van der Waals interaction or pi-pi stacking, and they form large complexes of supramolecular system. And these supramolecular systems are the main core of biological systems, starting from our DNA to protein structures, interaction between enzyme and its substrate, and even the phospholipid membranes present in our cell, they are all formed because of these supramolecular interactions. So more recently, these molecular machines were made by different scientists and different research groups. So these molecular machines also plays important role in our biological systems, and in the year of 2016, Professor Ben Feringa, Professor Sir Fraser Stoddart and Professor Jean Sauvage got Nobel Prize for building different molecular machines depending on the supramolecular chemistry. So they made different types of molecules which upon shining with light, they change their conformation, and using these light activated reactions you can form different type of machines or which can function differently presenting on the depending on the stimulus what you are giving. Like that, this is a kinesin protein which can bind to the microtubules, and in our body whatever transportation happens, that happens by this kinesin motor proteins which bind to the molecule which it wants to transport, and that can transport from different cells. So one of the most important part of supramolecular chemistry is host-guest interaction. So it depends on the molecular recognitions. These molecular recognitions are like lock and key. Like as we know, there will be a specific key for a specific lock. So like here also, if we take a host molecule and we can add a different library of different guest molecules into that, so the specific guest molecule which has the specific interaction with the host molecule, that will bind to the guest molecule, and by non-covalent interaction it will form a supramolecular complex. So in the host molecule whatever are already like available and the research are going on that. So cucurbituryl is another is a specific type of supramolecular host or macrocyclic host which is formed by the condensation reaction of glycouryl with formaldehydes. So it is called cucurbituryl because as we can see its shape is like a cucurbitum. In the cucurbituryl structures, CV7 or cucurbituryl 7, where 7 monomer glycouryl units are present, that is the most applicable in terms of research or biomedical applications because it has a wide range of guests available which have different range of affinity for the CV7 which can be easily tuned. It is highly water soluble. As we know, in our body most of the part is water. So whatever we are using for biomedical applications or forming some medicines or some bioimaging purpose, that has to be water soluble for its application. Then it is easily bioorthogonal, so it will not interrupt any inherent biological system and it can be easily functionalized also. So what happens, this is a adamantane molecule. It has high affinity as a guest for cucurbituryl. So when adamantane comes in with the reaction mixture in presence of cucurbituryl, it goes inside the cavity of cucurbituryl and water molecules which are already present inside the cucurbituryl, it comes out. So it is an entropy driven process, and here the terminal whatever carbonyl groups are present in the cucurbituryl structure, that forms a key role here, that interacts by a ion dipole interaction with the nitrogen atoms present in the this red color, this adamantane molecules. And inside the cavity of the CV7, as water is going out from the CV7 cavity, so this hydrophobic interaction between the adamantane and this cucurbituryl cavity, it will stabilize the supramolecular complex. Now it has different kind of applications. So using this cucurbituryl chemistry, we can do bioimaging inside cells. These are the mitochondria in our cells which are known as the powerhouse of our body. So from a single molecule using supramolecular interaction, we can go up to a self-assembled architectures. So how it can be possible? So if we take a molecular building block, first we can functionalize this building block, then we can self-assemble this using supramolecular chemistry. Or in another case, first we can self-assemble this molecular building blocks, then we can post-functionalize that supramolecular complex. So if we take a guest molecule and with that guest molecule we attach different length of alkyl chains and then we put CV7 into that. So what will happen, these guest molecules will come together and by the virtue of these alkyl chains by hydrophobic, self assembly means you have one molecule. So when these molecules come together by non-covalent interactions like pi-pi stacking or hydrophobic interactions or hydrogen bonding, they will assemble into a large molecular structure which is like connected with the non-covalent interactions, that is reversible interactions. Yes. So this by CV7 adamantane interaction and in this alkyl chains hydrophobic interaction, these self-assembled structures can be formed. These were different kind of self-assembled structures like 1D nanorods, 2D nanosheets and 3D micelle kind of structures can be formed. So then we can add different moieties to the CV7 and adamantane guests, so that by different kind of stimulus we can activate this system specifically. One of that is light activatable system. So how is it done? If we can conjugate a bulky group with the adamantane molecule, so what will happen? When it will try to go inside the CV7 cavity, it will feel some static hindrance. So it will not be able to go inside the CV7 cavity and will not get the desired complex. So what we can do, if we can specifically shine light on this molecule and then this bulky group can be removed, then easily this molecule will be captured by the CV7. Using these strategies, defined bioimaging purpose can be solved. So we can, what we can do essentially, we can add our CV7 molecules as Alka told using click chemistries to our cells and define cellular organelles, and then these adamantane molecules can be conjugated with the fluorophores and the bulky light sensitive group. So when this, you can see this before irradiation, when this bulky group is attached to the adamantane moiety, it will never go inside the CV7 and we will not get any signal in imaging in fluorescence microscopy. But once we shine light and this bulky group is clipped from the adamantane moiety, then it will easily go on inside the CV7 molecules. So as it is having a fluorophore attached to it, so we will see this good high background to signal ratio and our specific targets. Then as CV7 has a long range of guest binding affinity with it, so different guests can be reversibly bind to the CV7 moiety. So what will happen, if we take a guest which is having less binding affinity for CV7 than adamantane, when it is in the medium, this guest will bind to the CV7. This is called cyclooctyl amine. But when adamantane comes into the system, it will easily replace from this guest from the cavity and it will go inside the CV7 cavity, and it is having high affinity towards CV7. So using this strategy, different bioimaging purpose can be solved, like we can conjugate this low affinity guest with a quencher which can essentially turn off the fluorescence of a fluorophore molecule, and it will, when, and CV7 is complexed with a fluorophore molecule. So when this both the systems are in a complex, so this guest molecule will be inside the CV7 cavity and this fluorophore will be quenched because of the presence of the quencher in its near vicinity. But when the guest 2, that is a higher affinity guest, is put in the solution, what will happen, it will readily replace the medium affinity or low affinity guest from the CV7 cavity, and then the fluorescence will turn on. So this way we can specifically turn on the fluorescence whenever we want. And this strategy has its application in bioorthogonal host guest imaging, where we can essentially remove the non-specific signal by specifically turning on the fluorescence where we want. So this way we have done imaging of different cells and different cellular targets. Thank you. So now sir will continue with different applications which we are doing based on this supramolecular chemistry. Yeah. So as I told, sorry, so when both the systems are present in the solution, this adamantane and CV7, what will happen, this CV7 has a portal, carbonyl groups present in the portal, and these carbonyl groups are having high dipole moment. So this carbon will have a delta plus charge and oxygen will have a delta minus charge, and this adamantane is in presence of water, it will be in the protonated form. So adamantane's amine will having plus charge. So when this will be mixed in the solution, this adamantane's nitrogen will have a ion to dipole interaction with the carbonyl portals. And when this CV7 is not having any guest, water molecules are inside the cavity. So as soon as these are carbon based structures, so it will be very hydrophobic. So when it comes inside the CV7, these water molecules goes out. So that is called hydrophobic interaction. And as lot of water molecules are going out, so it is increasing the entropy of the system also. So by this way, this adamantane molecule will go and bind with the CV7 using non-covalent interaction. But as is this case, this adamantane is having high affinity towards CV7, so it will not be easily replaced from the CV7. But if we can use any low affinity guest, as I showed you, this cyclooctyl or cyclohexyl rings, so these can be easily replaced by reversible interaction using adamantanes. Not all are present, but some kind of these kind of structures or phenyl rings which are having affinity towards CV7, those are present, but this can be easily made and conjugated with the biomolecules present in our cells like proteins or DNAs, and can be transferred to the cell, because these are highly water soluble also, CV7. So
yeah, so I think in a basic language, self assembly is like assembly of human. So even you go to any marriage ceremony, marriage function, you will be always associated closely to your family, right? And you can always see that, you know, families are together. You go to with your friends to a mall, you will always be found together with your friends, right? So what is that bonding which is holding you together? That is the self assembly. So self assembly we see in real life, and this is the self assembly in molecular level. So what we see in real life is replicated in the molecular level. Similarly, in our body also there are molecules which does the similar thing, right? They know which molecule to bind, what to trigger, and how to proceed. And that's the form of life what we are talking about. And here we talk about lot of kinetics, thermodynamics, which are the driving force. And in real life it is also a similar language, right, where you feel comfortable, right? And how do these molecules find them together? I think it sort of tries to bind with many molecules, but once they find the better thermodynamic stability, they stay together, right? So it's driven by some sort of energy minimization. So similar way, like you always feel comfortable around mother, right? Even you go a lot of places, but you will always come back to your mother, right? So that's what it is. So just I will take few more minutes because time is running out. So what I wanted to tell you is that I started talking about different ways the carbon form bonds, what are the kind of applications they have. Then you have learned about different molecules, how they are made, what they behave. I will tell you a little bit what we are doing research in our laboratory using this organic chemistry. In simple, maybe in 5 minutes, I will give you an idea that where we are going and what is the research going on in the laboratories in today's world. So let me just go to the slide. So this tells you a very important phenomena about imaging. So we know what is imaging, right? We are always taking picture. That is the basic form of imaging, taking a picture. How do you really identify that today we have this many people present? You take a picture, you sort of look at it later, right? And to understand the biology or to understand what is happening with a living human being, you really need to take a snapshot or a picture, right? Then only you will be able to learn and understand. But the challenge what we all face is that we may be able to see an ant using our human eyes, we may be able to see a hair, we may be able to see a mammalian cell using a high-end microscope or a bacteria. But can we be able to capture a single small molecule which a nanometer size, right? A single protein molecule which is around 5 to 10 nanometer. What about the DNA? So these are much smaller than our abilities to visualize them. So now if we are discovering science and trying to understand how this molecule behaves, we need to have a picture taking mechanism or some abilities so that we can investigate these really small molecule which are less than 100 nanometer. It's like 10 nanometer, 1 nanometer. So how do you do that, right? So that's essentially an idea, or science is going towards looking at molecular level understanding of human being, understanding of the disease, understanding of the mechanism of an medicine. And that's how we work on, and we try to sort of use different organic molecules, and I will show you a very specific organic molecules and what it does, right? So what happens usually is that when you have a lot of molecules together, they basically sort of mix together and give you a structure which you don't know. But we were able to come up with a new sort of molecules where we can study them individually. And I will show you a video quickly, and I will try to wrap it up quickly. So this is what happens. Your molecule is there, and as this host guest self assembly as you are talking about happens, and as it happens you emit a light. And how it looks? So now you see what we are seeing here is an individual molecule. Have you guys ever seen a molecule? It's impossible to think about looking at. So this what you see here is coming from one individual molecule and binding. And what we will see is a very interesting behavior when we goes to molecular level, right? What you see is like flashing light, blinking, like the way stars blinks. And that is the behavior what we see when we actually go back in the molecular level. Isn't that like amazing, the way we look at the stars, and now we can replicate it in the laboratory using molecules. And that's what the beauty of the science we are exploring, and that is able to provide us a picture which we have taken using a very advanced microscope which is today, but tomorrow we are going to go with a much sharper image, with a much better clarity, just because we have the molecule behaves very differently and the way we want. Okay, so that's how we are going, and we have many new data looking at our resolutions of our microscope is currently 3.25 nanometer. Just think about what we are talking about. Close to a nanometer molecule we are able to observe. And again, these are the three-dimensional image of many of these structures. But one last thing I would like to show you is a diagnostics. How do you look at bacteria? Mycobacteria is very important, because there are a lot of disease burden of this mycobacteria, and we are able to now develop these molecules which lights up the specific microbacterium species, right? So if anybody is is sort of infected, we basically would be able to now localize and visualize how this mycobacterium behaves. And that's how it is that we develop molecule, we understand molecule, then we employ them to disease diagnostics all the way to therapeutic applications. With that, I think I would like to conclude here, and we would like to have the last quiz session, and that will be the last thing for today. Okay, welcome. So I welcome all of you to visit our lab. If you are interested, please send an email. I will be very happy to host you in our lab to show you some of the research, what is going on in our lab. You would also be able to talk to the students, and maybe it will help you to sort of see where the science is going and where India is sort of making a contribution to. Okay, let's join the last session of the quiz. Okay, I think everyone joined. Anyone? Okay, done. Let's start. Who shared the Nobel Prize 2022 for click chemistry? Wow, everyone is paying so much attention. I am so pleased. Thank you. What is the key interaction in supramolecular chemistry? Sorry. Okay, good, good. Srikara. Oh, okay, nice. Cucurbit will form host case complexes primarily through covalent bonds, radical coupling, electrolysis, ion dipole, and hydrophobic interactions. Wow, these are tough organic chemistry questions, I must tell you. If you go and ask anyone in the university also, they will not be able to answer this. So, oh, okay, so we have a new winner, seems like. Okay, let's continue. This is the last question of today, of this session as well as today. So please pay attention, and we'd like to see a new winner here. Okay. Copper click reaction. Wow, okay. So this was tough. Kritik. Second, Srikara. First is Radhika. Oh, we have, who is Radhika? Oh, nice. Can you please come here? Have new place. Could you please tell about where are you coming from and what are you currently doing?
I'm from Bangalore and housewife.
Oh, okay, nice. At least science you like, right?
Yeah, I'm very curious about science.
Okay, very nice, and we are very happy to see you. We have a small gift. Okay, thank you. Yeah, of course.
Thank you. This is not so clear. Thank you.
Thank you. Okay, with this we'd like to conclude the session, and if there is any question, we'll also be happy to take. If there is something which you would like me to clarify. Yes, please.
In the second lecture, they told that when you excite the electron, it jumps. So if you excite it with red light, it will give you back blue or some other color light.
No.
Not like that.
No. So it will, if you excite the electron, it goes to the excited state, and it requires a specific wavelength of light, which depends on the energy difference between the excited state and ground state. So that's why the light is called quantized. So it's like a packet of light. Either you take a packet or you don't take a packet. And then what happens that once you give the light, when it comes back, they will have less energy as compared to the light what you have given. So if you are giving a blue light, which are usually lower wavelength, right, you will get a higher wavelength light, you will get a red light. Understand? So, the energy of the photon which are emitting is the lower in energy and higher in wavelength.
What happens to that other energy?
A very good question. So, when someone is in excited states, right, what they do? They vibrate, right?
Oh, heat energy.
So when they vibrate, they dissipate some energy. So before they actually come back, they lose some energy in the excited state, right? So don't try to be always in the excited state because you will be losing energy. So better to be in the ground state. Okay, any other question? Yes, please.
So carbon is one molecule, but how could it form so many different things?
Carbon is an atom, right? Carbon is not molecule, first of all. So it makes molecule by bridging with multiple other atoms, let it be its own carbon or oxygen or nitrogen or diversity of the bonds between carbon to carbon or carbon to other element. So it's not one atom we are talking about, it's the aggregation of multiple atoms together and making a bond, making a molecule. And you can think about that how many ways you can actually bond, right? So within this room, if you try to make molecules, there could be, pair of 2, pair of 3, pair of 4, pair of 5, then, different molecules, different people come together. So that's how it can have so much diversity around. So that's what the carbon about, right? It's not one, it's atom connecting different components together, right? Any other question? Okay, so thank you very much. Yeah, sure, please.
I'm really happy, sir. Myself, I am Srinivas, and you people are a very young team. Like we are in the 78th year of this freedom. What we call as independence. So it's so nice to see the youngsters go into a very bigger stage, because you have been occupying the central stage in explaining so many things about science. So what I feel that we have been very ignorant about all these things, because we have not been exposed to those, the kind of instrumentation and the kind of knowledge with all these YouTubes and other things. We were just textbook oriented learning, even 3D was very different in our age. So one thing what I felt is color means we should have our eye, optic nerves, and that's very important.
That's correct.
Perhaps a blind person cannot understand anything what he says. So that is very unfortunate in the human side.
Yes.
But the other side is, I felt that Sir C.V. Raman would have been very, very happy that he has got so many students now. Right?
That's correct, yes.
So he was a person who did a lot of experiments with his color.
Yes.
And I am sure that many people should visit Raman Institute. Perhaps your information will be much more useful there, because you are doing a lot of
yes, interaction of light and matter. So light and matter interaction.
I just wanted one more thing. What about this fluorescence of animals and things like that? I think that is one thing which I just wanted to ask, sir.
Yes, that's correct. So as we showed that the molecules which are inherent fluorescence, right, if it is expressed or if it's produced by the animals or even marine animals, actually that the Nobel Prize in the fluorescence field has gone to someone discovering a fluorophore from jellyfish. So jellyfish is the one which has given us abilities to start looking at biological molecule which are fluorescence. It's called green fluorescence protein, right? And so that means that nature has given us everything. It is just our eyes to pick up that what we want to extract, right? And even I can tell you that today also we always try to think to the basics, that what nature is and what is the basics we can learn. And in this age where we are always in sort of social media and YouTubes and things like that, I suggest all of you to walk outside and look at the nature and enjoy. And I think the great science can come from there, as it has been shown to you that from the medicine it started. As you can see that the medicines of aspirin started from nature, as you rightly pointed out, fluorescence molecule started from this jellyfish. So I think almost everything, nature has the answer. We just have to find it, right? So, okay, thank you very much.
Hello. I'm sure that all of you wonderfully enjoyed this. You see, I really feel bad for many people who have missed this lecture session. In fact, this was one of the finest, not only in Dasara Lecture Series, anywhere in my life, I would say. It was most interesting. You know, Professor Agasti, in addition to he being a very good communicator, and he gave opportunity for his juniors, his students. And third thing is the involvement of, the audience also was very much there through quiz. In fact, this is a fantastic format. In fact, really, I feel pity for the people who missed it today. But at least, let us say, in our YouTube channel, they are going to see it. And one more thing which I wanted to mention was, they say a picture is better than 10,000 words. And I have extrapolated it as a moving picture is better than 100,000 words. You saw the wonderful animations, what they showed. In fact, how things, see, it's always different. What you do at laboratory level is different from what it goes to industry. In fact, all these things, but at the same time, all these colorful things, at the same time, you have to study science with interest. That was also emphasized in the talk. Thank you, sir. Thank you very much for you and your team for coming here today, accepting our invitation, and making this happen, and gracing the occasion, and wonderfully conducting this session. And let me also thank, today I saw the transmission in the YouTube channel. The picture was crystal clear and the voice was very clear. I am sure that people in the YouTube channel, they are going to enjoy. And let me thank our team for doing this. Really, it is an in-house effort. So all of them, all the people who have worked for this, I thank. And I would request all the people here today to come to our programs in large numbers. In fact, such things, in the tailor-made things are available in the internet, and which is good, which is bad, nobody knows. Everything you feel to believe that, you feel like believing, but that is not the case. These kind of things go a long way, and they are the people who are busy with their own work, and they have been kind enough. Professor Agasti has been kind enough, and his students, along with his students, he has designed a format and done that. Thank you, sir. Thank you very much. With this year's Dasara lectures has come to an end, this series. And the theme was carbon once again, and 4 aspects of carbon: carbon in life, as well as carbon in organic chemistry today, and carbon in climate change, as well as carbon in nanoscience and technology. I hope it was enjoyable, and thank you very much once again for all the people who have been responsible for this, without forgetting Professor Agasti today for chairing, for delivering a talk in this concluding session. Thank you, sir. And high tea is waiting outside. Kindly do have it before going. Thank you very much once again.